Hello everyone, this is lecture 16 for the atomic physics. In the last lecture we have completed the LS coupling and we have seen how to find the ground state and all, and we have already seen the some questions also. So today we will start the JJ coupling. So that is, first we will see for the non-equivalent electrons. So like this we have 4p1 4d1. Now when this JJ coupling happen, means I told you that as when A is greater than 32, then mostly this superimpose or dominate on the LS coupling. So what happens when it JJ coupling occur? So first L1 and S1 we will write for this. So L1 is 1 and S1 is half for this one, this electron. Similarly for this D, it will be L2 will be 2 and S2 will be half. Now in the LS coupling we have seen that they are first means this is L1 plus L2 all will combine to give some L, then S1 S2 will combine to give some S, and then they couple. But now in the JJ coupling they will first give some J1 and this will give some J2, then they will combine or couple together J all J's and give you the J values. So that's how the splitting take place in the multi-electron system for this kind of JJ coupling. So like this, let's see for this, L1 is 1, S1 is half, so J1 is L1 plus S1 to L1 means L1 minus S1 to L1 plus S1, so it will be half 3 by 2. Similarly for this it will be 3 by 2 5 by 2. Now how they pair up? So to couple up J1 and J2, so we'll write 1 by 2 with both of them and 3 by 2 with both of them. So it will be like this, 1 by 2 3 by 2, 1 by 2 5 by 2, 3 by 2 3 by 2, and 3 by 2 5 by 2. Now how you can find the J? So J values will go from J1 minus J2 to J1 plus J2. That means 1 by 2 minus 3 by 2 to 1 by 2 plus 3 by 2. So that will give us 1 to 1 and 2. Here they will give 2 and 3. Here 0 1 2 3 and 1 2 3 4. So that's how you'll get these 4 values. Now how you can arrange them in the energy level? So the minimum J values will give you the minimum state. So first you will see that which J is very less, so that is 1 by 2 in comparison to 3 by 2 3 by 2. So in 1 by 2 1 by 2 you will see that 3 by 2 is less, so this will give you the lowest state. And now this will split into 1 and 2. And similarly next one is this one, so it will be 1 by 2 5 by 2, then it will split into 2 and 3. Then this 3 by 2 3 by 2 will give you these 4 states, and this will give you these 4 lines. Okay, so that's how they split up, and this is how the non and for non equivalent electrons JJ coupling occurs. Okay, now important thing is they can ask you for the equivalent electrons, so you must remember these rules. So when J1 is not equal to J2, then this will happen like this, coupling will be like same here. But when J1 equal to J2, then the rule will be like J values will be 2J minus 1 to up to when this becomes 0. Okay, so it can be if J is half, then it will become 0 in the first place, so J will be only 0, but it can be 0 at any point. Okay, so that's how you will get the J values when J1 equal to J2 in the equivalent electrons. When J1 is not equal to J2, values of J will be found by the rules of coupling for the angular momentum. So let's see, take an example first. So let's just like you have P2, so these both electrons are in the same subcell, that's why we are calling them the equivalent electrons. So L1 is 1, S1 is half, so J1 can be 1 by 2 3 by 2, and L2 is 1, S2 is half, so J2 can be 1 by 2 3 by 2. So let's couple them, they will give you these 4 pairs, 1 by 2 1 by 2 1 by 2 3 by 2 3 by 2 1 by 2 3 by 2 3 by 2. Now this can give you, means now you see that both J are same, so it will be like go from 2J minus 1. So first write J as half, that will give you 0. So it is only J, only one value will be there, because there can't be 2J minus 3, that will go into negative. So when you will get 0, then you will just end the series there. 1 by 2 3 by 2, they are both are different, so you will do the simple coupling, that is 1 by 2 minus 3 by 2 to 1 by 2 plus 3 by 2, that will give you 1 and 2. Similarly here also you will get 1 and 2, but here J is same, so it will be 2J minus 1, that will give you 2 first, then the next one 2J minus 3, so 2J minus 3 will give you 0, so means it will end at means second one, so it will be 2 and 0. So these are the J values, and here J are the values. Now similarly you have all the J values for different coupling, and you can just split them same. So that's all here in the JJ coupling. They can ask you only this based on this rule basically, so you must remember these. Now today we will start the Zeeman effect. So what is the Zeeman effect? See, normally we have seen the fine structure, and there was this internal magnetic field. But what happens if you apply some external magnetic field in the system? Then there will be multiple splitting will take place. Means again you will see that lines will split up furthermore. So, and there it depends on that how the magnetic field is present, means it can be strong magnetic field or weak magnetic field. Based on that the splitting will take place, and based on that we derive these three effects, that is normal Zeeman effect, anomalous Zeeman effect, and Pasternak effect. So what is this? It is a modification of atomic fine spectrum by the application of magnetic field. On applying magnetic field, actually three different effects appear depending upon the condition. So what are the conditions? there can be weak magnetic field. When there is weak magnetic field, there will be two conditions: when spin is equal to 0 or multiplicity equal to 1, and when spin is not equal to 0 or multiplicity is not equal to 1. So these are the two cases when B external is less than B internal, and we'll discuss these two cases. So there will be some splitting. And then second case, when B external is greater than B internal, so there will be, it can be for S equal to 0, S not equal to 0, so both of them. So we'll discuss them all the three in detail. So first, let's take a brief idea of all these three. So in the normal Zeeman effect, you will get three equally spaced lines in the spectrum. So there will be further splitting, and then you will get these three lines which are equally spaced, and difference will be, you can find easily. So you will see them that you will get three spaced lines, equally spaced lines. In that you will call first one as plane polarized. We denote the plane polarized lines as pi, and you don't need to go into the detail of these polarizations. So you just remember that pi represents plane polarized light, and sigma represents circularly polarized. This is right and the left polarized. So these three lines you will get in the normal Zeeman effect. So it will always be three. Okay. And in the NML's Zeeman effect, there will be a complex spectrum you will get. So it won't be fixed that how many lines you will get. It can be any number. And the last is, that is Pasternak effect. We will see that there we will get three lines. So that's how in these three we will study that how we are getting these three lines in the detail. So let's start with the normal Zeeman effect. So this effect occurs when S equal to 0. So it takes place when spectral terms have multiplicity equal to 1, means S equal to 0 will give multiplicity 1 when a weak magnetic field is applied. It means there is only atomic magnetic, means now you will see that S equal to 0. So mu s must be equal to 0 because the formula of mu s is E by 2m s. So S is 0 will give us mu s equal to 0. So there will be only orbital magnetic moment is present, and there will be this some external field is applied. So that will couple with this orbital magnetic moment, and that will give us the potential energy difference, and that's how splitting is taking place. So it means there will be only atomic magnetic moment when placed in a magnetic field. It will behave like magnetic dipole having mutual magnetic moment. It will interact with the B external and give rise to perturbation energy, that is potential energy, as follows. So as I told you, this is the same thing. Now there is this magnetic moment, and wherever the direction of magnetic field is, we will consider that direction as Z. So that is now as isotropy is broken. So U is minus mu L B external, and mu L in the direction of Z we need to find. So it will be mu L Z B external. And now let's find first mu L Z. So mu L is minus E by 2m L, as we know the formula. G is 1 for L. And now we need to find the component in the Z direction. So L is also quantized in Z direction. So LZ is nothing but ml h cut. This is this, and this is your Bohr magneton. So it will be minus ml mu b. So you have mu lz, just multiply with b external, you will get u. So it will be minus plus, and u will be minus ml mu b b external. So this is the number, means this is the perturbation. And now based on the different values of ml, you will get the different lines. Means for L equal to 1, you will get 1 mu b b external, 0 mu b external, and minus mu b external. So these three lines you will get. So that's how the splitting will take place. Let's see. If you have L equal to 1, then ML can be plus 1, 0, minus 1. So U values can be, for 0 it will be 0, and for 1 it will be plus mu b b external, and for minus it will be minus mu b b external. So that's how these three splitting will take place in the P. So you will get these three. And similarly for L equal to 2, it can be 0, plus minus 1, plus minus 2. ML can be this. So energies can be, means these splitting can be this, like this. This is because of this perturbation. And now at this, you will be plus 2 mu b b external, and you will see here that this difference is already same. Mu b external, this energy is remaining same, and this difference is also mu b b external. So that's how we are getting the equally spaced lines. So they are same. Now there is this transition. Let's see how we are getting these three lines. So let's see that if transition is taking place from 1D2 to 1P1. See, this is showing us that it is normal Zeeman effect. Why? Because this multiplicity is 1, that's why it is normal Zeeman effect. So for this L equal to 2, we have these 5 lines, and this P we have these 3 lines. And now for this transition, they must follow some rules. So again the same rules, but here there is rule for ML also, means delta ML can be 0 or plus minus 1. So you must remember this, that delta ML can be 0 or plus minus 1 in the normal Zeeman effect. Or when this difference is plus 1, means it is decreasing by 1, that will give us sigma plus lines. And when difference is increased by, means decreased by minus 1, that will give us sigma negative. And when difference is 0, that will give us pi lines. So let's see. Now if you have this L equal to 2 and it is L equal to 1, so this difference is 1 and it is decreasing by 1, so this will give us the same line, that is sigma positive. And again this for 1 to 0 also you will get the same frequency, and here also you will get the same frequency. That's why we can just combine these three lines into the same, because they will have the same frequency or the energy. That's why they can't be split, and they will give us a single line, that is sigma positive. Similarly here similarly here we are getting 1 to 1, that will give us 0, and here also 0 to 0 is 0, and minus 1 to minus 1 0, means the difference is 0 delta m. So this transition is also possible, and all these three lines will have the same frequency. That's why we are having this single line as pi. And now here it is 0 to 1, that is increased by 1, and here it is minus 1 to 0 increased by 1, and here minus 2 to minus 1 increased by 1. So all these three lines will have the same frequency. That's why this will give us a single line, that is sigma negative. So that's how we are getting only three lines. And if this difference is h nu naught, then if you find the energy for this line, then how much it will be, you will see that here it is a 2 mu b external, and here it is this difference is 1 mu b external, and this is 2 mu b external. So net difference will be 1 mu b external plus this h nu naught. So that's how the frequency will be h nu equal to h nu naught plus mu b external for this line, this sigma positive. This will be your frequency, means this is your energy, how it will be. And now from here you can find the frequency of these lines. This will remain same for all these three, so that will be mu naught plus mu b external divided by h. And now h nu equal to h nu naught for this, means you can see here this is only 1 up here, and here also 1 up, so it will be same energy as here. So h nu equal to h nu naught, so nu will be mu naught. And similarly for this, you will see that it is this is just the difference is 1 mu b external, means this difference is h nu naught minus mu b external, this difference equal to that. So that's how you can find h nu negative, sorry, sigma negative will be h nu naught minus mu b external. From here you can find the frequency of these lines also, that will be this. So now you have the frequency of all these three lines, and this is increased frequency, this is decreased frequency, and this will remain same, the same frequency. So that's how you are getting the three lines based, I mean three frequency you are getting. So that's why you have getting the three lines. Now see, if you need to find this how much frequency is increased, means here you are getting the same frequency like here for this transition. But now if this is giving you some higher frequency, so how much higher it is? So from here you can see delta mu, this mu minus mu naught will be mu b external divided by h. So delta mu will be mu b external divided by h. Now just substitute the value of Bohr magneton, that is E h cut by 2m. So it will be, now substitute the value for h cut, that is h by 2 pi. So that will give you 4 pi m here, and h will cancel out. So this will be your delta mu. So you must remember this is the frequency difference. If b external is given, you can just substitute the value and you can find the delta mu. And again delta mu is minus c by lambda square delta lambda. So c equal to mu lambda, from there you can find this formula very easily. So delta mu will be this, and from here delta lambda will be minus lambda square by c delta mu. So this will be minus plus, and this will be lambda square by c e external 4 pi m. So this will be your delta lambda. So you must remember these two formulas, that is delta mu and delta lambda. And there is one more thing, that is term value. And what is term value? I already told you what is term value, but here also let's define it again. That is E by SC. Now unit of this is meter inverse, means energy normally you get in joule, but E by SC you will get in meter inverse. So E is SC by lambda, so SC will cancel out, you will get 1 upon lambda, and this has a unit of meter inverse. That is why this term value has a unit of meter inverse. Now see how can we write these results in terms of the term value. So from here you can find that du is equal to minus 1 upon lambda square delta lambda, and you can just substitute the value of delta lambda from here, this one, and this will give you this E b external 4 by mc. So this will be your term value, this is your term value. And now if you see that these all are constant other than b external, so term value is 46.7 b external. So this is a very important formula to find the term value. And now how it help you, if you have the term value, then just delta lambda will be lambda square term value. You can see here this delta lambda is equal to lambda square, means this thing is simply term value. So that's why lambda square, this term value will give you delta lambda. And you can see here delta mu, this is if you just divide by c, and then you will get the term value. That's why this is equal to c multiply the c term value will give you delta mu. Okay, means just this is your term value, multiply the c here, c will cancel out, and whatever remaining is your delta mu, you can see here. So that's how they are related. So if you know the value of term value, just b external will be given, just multiply with the 46.7 and you will get the term value. Substitute it here, lambda will be given for this particular range. This lambda will be given, and you can find the what is the delta lambda and delta mu you can find with the help of the term value. So you must remember these formulas, very important. So that's all for today. Thank you everyone.